Welcome to Vision Summit 2026. I, your host, MC Akshay, once again take this opportunity to welcome each one of you present here to an amazing, meaningful interaction session that we will be starting off with. Leveraging RISC-V as a unified, heterogeneous hardware and software platform for the next gen AI chips is what we are all here for. So I would take a minute to quickly run through the session, what you can expect from the session. This is a seminar on RISC-V architecture in building the next generation artificial intelligence chips and how Akeana is enabling it. This session will give you the required information about the advantages of a heterogeneous artificial intelligence silicon with RISC-V along with the additional technologies, general architecture of how a heterogeneous system would look like, and Akeana's architectural implementation solution on the same. Taking a minute to talk about the company, Akeana RISC-V startup was founded in the year early 2021 by the leaders in the industry. Akeana's semiconductor IP offering includes low-end microcontroller cores, mid-range embedded cores, and high-end laptop server cores, along with co-inherent and non-co-inherent accelerators as well. Now, for the seminar, I would take this opportunity to introduce our esteemed speaker, Nitin Rajmohan, who is a design verification leader and has a long track record of building large multi-site validation teams, validating complex cores and producing high-quality silicon. Most recently, Nitin was the Senior Director of Verification on the ARM server program at Marvell and led core validation on the Thunder X3 program. Prior to Thunder X3 program, Nitin led core validation on Thunder X2 at Broadcom and later Cavium and Marvell as well. Nitin has also led core validation on MIPS-based designs at Broadcom, NetLogic, and worked on x86 validation at Intel. So that gives us an amazing opportunity to have a speaker representative from Akeana joining us on the stage. Ladies and gentlemen, can we give a warm round of applause and welcome Sir Nitin on the stage, please.
Good afternoon, everybody. How's everybody doing? Good, good. So first of all, I'm honored to be here, in the eastern capital of tech capital on the Eastern world. So glad to be here, present here, and giving this talk here. So today's talk is about how RISC-V can be used to build advanced AI chips using a unified heterogeneous architecture. And the way we will walk through is that the advantages of RISC-V, we'll talk about why RISC-V, what value it brings into the table, and what are the different ways you can put together a heterogeneous architecture for AI, and how do you go about building such an architecture into actual subsystem on a chip. Okay, let's get started. A bit about the company. So Akeana was founded nearly 5 years back. It's a venture capital-backed startup. We are a processor and AI IP solutions company, RISC-V ISA-based. The team was formed with leaders from different tech companies in the semiconductor space, mostly from the Thunder X2 ARM server program. One of the flagship products is a high-performance CPU, 25 spec-int, for the RISC-V space. We also enable customers for different cores and interconnects, coherent, non-coherent, and system IP. Everything readily available now. Target applications include high-performance, out-of-order cores, data center, HPC, automotive, mobile, client, wireless. Our offerings span the whole space on the CPU compute area. We also then have targeted AI products, AI cores that target the AI market. We got a very robust compliance and verification process. We are RVA 23 compliant. RISC-V, Vector 1.0 spec, AIA, MMU, AMBA, we are compliant to all these standards. Again, tier 1 investors, a long runway, been around for 5 years, and expect to be here longer, much longer than that. So. Okay, let's talk about AI, right? So the AI CPU compute, so AI itself is a very nascent technology that's growing at a rapid pace. It's changing on a daily basis. The way the technology is being used, and what is the priority, in terms of the technology for AI silicon. I mean, recently you might have seen the news from NVIDIA, where they announced that they're going to, the next generation Vera Rubin chip, a platform, is going to have SMT. Now, SMT is a very critical feature. I'll talk more about what SMT means. SMT means simultaneous multi-threading feature. And NVIDIA's, traditionally, there's always camps on both sides. There's one camp saying that SMT is the way to go, and another camp says that, no, we don't believe in SMT. This has been happening on the data center. And now, the AI, we had a similar, what you call, back and forth on that. And NVIDIA taking the stand kind of validates the importance of AI. And we'll show you, we'll see how AI can utilize the multi-threading capabilities. And by the way, we are one of the first pioneers of multi-threading technology for the ARM and for the RISC-V also. Ours was the probably the only ARM server with multi-threading technology. So, and then, with this kind of technology change, what we are expecting is the AI SoC developers to be starting to push performance using this technology. So, and feel free to stop me anytime. I'd like to keep it interactive. If you have any questions, just stop me right there, and I'll be glad to answer it. So AI market range and needs. Again, it's a very broad market when you talk about AI silicon. You got wide range of devices and applications. You got all the way from the data center to the edge, right? And then in between, automotive is there. There is security type applications. Each of those require a different performance, different latency, power. The requirements varies over these different spaces. You got, right now the latest in is generative AI, ultra-scale generative AI, where a lot of the attention is going, moving away from training into generative AI. But also, a lot of the focus attention is also on the edge devices. There are different market space specific constraints. I talked about it. You got, each space has its own performance and power requirements. And also different types of devices. You got GPU type devices, TPUs, another CIM. CIM is compute and memory architecture. So there are different architectures that cover that. One of the latest challenges, it used to be power and data movement. Now the biggest challenge is what they call is the data movement. They call it the memory wall, if you might have heard of it. So data movement is a big challenge because now you got compute moving ahead fairly fast. How do you supply data into this compute engine without any blocks and very low latency? And you'll see how a heterogeneous architecture can be leveraged to be able to build this, address this data movement bottleneck. So before we get into heterogeneous, why RISC-V? It's a very natural fit for AI silicon. RISC-V has its open ISA standard, so which means that it's like the Linux of hardware, right? Now, how when Linux came, it was a big revolution. Similarly, RISC-V is kind of creating that revolution, right? You got this strong open hardware-software co-development. So development happens very fast. It moves at a very fast pace. It also simplifies. So since AI is going through a massive changes on a daily basis, it simplifies building AI-specific models and software because you need to move fast with the changes happening. The other aspect, because it's an open source architecture, you have options for multiple IP sources, which means you get cost benefit. Now you can find the right IP, CPU IP that meets your performance, PPA needs, application needs, market needs. There's a lot more option. And obviously, there's a cost benefit because there is no architecture license. You need to pay for it. So you get a cost benefit also. So the other big thing is there is no architecture baggage. RISC-V is a fairly new architecture, maybe 10, 15 years old. It is built ground up. So it doesn't have the legacy architecture that a lot of the other architecture like x86 or ARM come with it. So you can build silicon that you want without having to worry about supporting legacy. You can build silicon efficiently. It's a lean design. So you don't need to spend more area, more resources, and more time to build the capability that you want and move very fast. And it's a greenfield software development because it's a ground-up architecture. There is, when you compare to other established architectures, they're all starting from a very similar space. It's not like there's one architecture that has a necessary advantage after another when it comes to software development. So that's on that. And then RISC-V, the way it is designed, it's a very modular architecture. So they have this concept of extensions. You can, every piece of, every feature is compiled as a set of extensions. And you can pick and choose the extensions you want. And this is great because when you're building a heterogeneous architecture, you don't want like one CPU doing multiple things, but having the same feature set, the bulk of features that you might not even use. So you can build a very efficient heterogeneous architecture, system architecture, with this modular architecture that RISC-V provides. It leads to better PPA, better cost, overall better advantage to your silicon. So the other thing about RISC-V, so you have the ability to do domain-specific acceleration. What does that mean? RISC-V is one of the architecture where you can put in custom instructions. Now, you cannot do that for ARM or x86. So what that means is that you can put in, again, because the technology, AI technology is changing so rapidly, you want to be able to add custom instructions that accelerate, provide performance to specific AI functions. And you can do that. Everybody can choose to implement. And still be RISC-V, you got the broad architecture compliance. So it means that a large part of the software is going to just run seamlessly. And still, if you want to use these special instructions, you can develop software to utilize these instructions, custom instructions. It's a way to future-proof technology, right? Especially on a massively changing technology like AI. The other thing is RISC-V vector extensions. This is, vector operations are the heartbeat of any inference. You need to have, and it varies. You can have a narrow vector, medium-sized vector, broad vector width. And it is critical to have a very highly performant AI software. And RISC-V provides this capability as part of the spec. The nice thing about this is it's a very scalable vector length you can use. So you can build, again, a heterogeneous architecture with different vector lengths for different types of operations and functions. And now you can put it all in a single system, and it will look like a single, you can use a single software base to be able to use all these system components. It provides flexible data types. So RISC-V is already widely adopted. And to name a few, Google, Meta, NVIDIA are already starting to use RISC-V. And it is rapidly becoming the de facto architecture for AI. Okay, let's talk about what heterogeneous architecture here means, right? So if you take a AI system, and I'm going to pick an example, let's say NVIDIA's Vera Rubin, or the older one, Blackwell, or Grace Hopper. You got a general CPU compute, and then you got the AI compute. Now, in the NVIDIA's case, in the general compute is ARM architecture, and the AI compute is their GPU, two separate different architectures. So you need to have software that talk to each other. It's not easy to have them talk to each other. I mean, to give them credit, they've been working on it for a long time. But if you look at RISC-V, now we can do the same thing, but using the same RISC-V architecture for the general purpose compute that does all the supervision tasks, coordination of tasks of the different AI functions. The general purpose compute can take care of it. So it's a homogeneous, multi-core, potentially multi-threaded systems. And then you got the heterogeneous data compute, AI compute system, where you have a mix of different core types targeting different AI functions. And the beauty of this is that you have a compute domain where all software is based off a single architecture. And you can pick and choose based on the code you're running different functions that you need. It makes the overall software development cycle much simpler, much easier, and much optimized. You can do that. So let's look at this AI. We're going to focus more on the AI heterogeneous data compute. I talked about the general purpose compute. We'll talk about it a little bit more. So if you look at the AI data compute, you got a control core, you got a AI processing element, then you got an AI data movement engine, then you have the interconnect fabric, you got a system controller, you got the AI accelerators. We'll talk about a bit about each of those. You got the AI control core. The AI control core is kind of like the one that takes data, gets it into a format that your AI compute can use, feeds it in. I mean, gets it formatted and gets it ready for the AI compute operation. And then you got the AI processing element. So this is integrated with the actual, what you call the GEM engine. We call it the GEM engine, which is a matrix multiplication. That is the heart of any AI operation, is the matrix multiplication. So this AI processing, AI compute element will talk closely with coordinate with the GEM engine, make sure that data is being fed properly to it, and the compute's moving through fine, right? That coordination it does. Then you got the AI data movement engine. Now, the purpose of the data movement engine would be to supply data at a very high speed. So you need to have a very wide vector, wide bus length to keep your GEM engines, the matrix multiplication engines, constantly working without any blocks, any stalls. You got the data interconnect fabric. Now you need to supply this data. You need a fabric that is high speed, that is multi-channel, that is pretty wide. So you can keep feeding your beast. This is the matrix multiplication accelerator. And once it does the processing, it comes back to the AI processing element, data movement, and then that goes back into the AI control core. So it's all targeting different aspects of the AI compute, but working together as a single architecture. Oh, and you got the system management. That does, you want to handle interrupts, you want to handle power, you got a small system control, a system management core. That again can be a RISC-V core. So that's typically a RISC-V, 32-bit RISC-V core. So you can see how this all fits together. Okay, let's see. So typically, if you look at it here, your control core, you have a few, your matrix multiply is the big bulk of it. You got the data movement core, that's going to feed the data into the matrix engine. Then you got the multiplication accelerator. You got the AI processing element, which is the bulk of it. And obviously, you need all these connected through a data interconnect fabric. Okay, well, no silicon story is complete without the actual software. I mean, I would say software is the most important part of it because, a silicon is just paperweight without the right software running on it. So the software is key, and the way it works is the RISC-V. You got these different software stack layers. You got at the lowest level, you got the actual hardware. Then when you go one level up, you got the firmware, and then you got the LLVM. LLVM is the compiler, open source compiler, that takes high-level software code, compiles into machine code, and feeds it in. And that has to be optimized for the hardware. Then you go one level up. You got the machine learning libraries and compilers. So those are basically stand in between the neural network frameworks and the LLVM compiler. So it takes the neural network framework, like coming out of the transformer, and then makes it more, uses the hardware features, gets a compiled, very efficient code, feeds it into the LLVM that will convert into machine code. You got the NN frameworks, which is the neural network frameworks, that talks to the actual application, LLMs, SLMs, that go on top of it. So the whole software stack looks like, and you got the Linux kernel, you got the kernel library, that oversees the whole operation. You got a debugger to connect to the hardware debug. I mean, if you look at it, the whole unified tool chain in having a single ISA is of a pretty big advantage. You can reuse code. It's optimized for power and performance. And you got the open source software ecosystem RISE that you can leverage off. Again, you can get your software developed very soon. All transforms into time to market, which is critical. So, which is what is going to help you get successful if you're building AI silicon. So a little bit about SMT. I talked about it, multi-threading. So what is SMT? SMT is simultaneous multi-threading. So what it does, you can look at this first picture on top. This is a processor without multi-threading. If you want to do 2 threads, going through the same processor, you got to do task switching. There's a software layer, and you got to do it serially because you can't leverage of this. So what happens is that if you have thread 1, for example, waiting on some data to come back, you got thread 2 waiting behind it because it can't do anything about it because thread 1 is blocking all the resources. Now, some of it is addressed through out-of-order processing, but what happens is that even out-of-order cannot completely address this problem. So now you come to a simultaneous multi-threading, where what you can do, let's say thread 1 is going through, it's using some hardware resources, and it's waiting for its data. So there are other hardware resources that are freed up that thread 2 doesn't need the hardware resources used by thread 1. So you can feed it in, and you have actually both these threads operating in parallel. So you get quite a bit of efficiency in your hardware, and you got, typically, I'll talk about the speedups we get. It improves your overall performance, especially when you have a deeply multi-threaded software. So how does multi-threading help? Scalar compute, if you're out of order process, we typically see 30% speed up using the same hardware. So you get a 10% hardware overhead, 30% better performance. When you do vector and data compute for an in-order processor, we see 125% performance improvement. And then, if you're doing an accelerator, it's multitasking is natively enabled. If you have data throughput efficiency, a lot of the latencies are hit because of multi-threading. So overall, SMT, kind of brings together all the technologies and accelerates AI compute and AI data movement. A little bit about the Akeana product lines. We have the 100 series. That is like the 32-bit microcontroller, embedded processors. Then you got the 1000 series. A lot of our AI compute falls under this series. It's in order, supports up to 64-bit addressing. Could be up to 1 to 4 wide, 12 stage. We also support out-of-order, slightly lower performance out-of-order this series. It got level 1, level 2 caches. The key is vector extension. It can support up to 2048 with vector extension, and it also has native multi-threading support. Then you go up, in terms of performance, you go to the 5000 series. This is a general compute, high-end data center class processor. It has all the architectural features that it support. This is the nice thing about it. They have the same architectural features, except it has a lot more performance features that can scale performance all the way up to ARM Neoverse type series. So let's talk a bit about the next generation AI general purpose compute. AI is increasingly, it's a mix of, I talked about a general purpose compute and AI data compute using hostless cases, which means that there is no actual OS running, and then you can seamlessly use these two types of systems. So when you look at what you call a general purpose compute, where it will be useful is if you have agents running. This will be like agentic supervisor, that will actually control the agents running in all these AI compute engines. You need a high performance management core, general purpose core that can manage all these operations and make sure that it's performant, it's operating smooth without any issues. So we have very targeted cores for this. That's the 5000 series I talked about. They have vector support, multi-threading, enterprise class. It's got the RAS and security and all the telemetry features. And we also have, you have to connect all these cores together. We have the interconnect, coherent mesh interconnect that can scale up to, it uses the AMBA CHI protocol, scale up to 1,000 CPUs connected together. So now coming to the AI aspect of it, which is the true heterogeneous computing here. We have the 1000 series cores. That, one of the what you call a differentiator for us is we have our cores are heavily configurable. So we can take the core and create different AI core types using a single core by configuring with the right parameters. So if you want the AI control core, very wide vector length. It's got AI-specific targeted acceleration. We talked about it. Multi-threading comes with it. Then you got a vector processing engine. It can go even wider vector, very low latency. It's got a close coupled memory sitting next to it, so you can supply data to it at very high speed, low latency. Then you got the actual data movement engine. That is basically, doing processing data from one format into another that you can feed into your vector engine and also your matrix multiply engine. So all these cores, when configured and put together, creates the heterogeneous architecture, a system architecture that we that benefits overall AI systems. Here's a complete view of all the different pieces, that goes into an AI compute and data IP, right? You got the out of order, I talked about general purpose core, very high performance, in order AI cores, control core, vector processor, data movement engine. You got the GEM, which is the matrix multiplication engine, the AI accelerator. The nice thing about it is because we support standard interfaces, a lot of times customers come and say, hey, we don't want to use your matrix. We have our own secret sauce. So we want to be able to use it. So we say, no, of course. So we provide the capability to be able to plug in a customer or a partner AI accelerator into our own subsystems to create the whole chip in a very seamless, very fast, easy way. And that's a significant value add to any customer who wants to build a RISC-V system. It's a single RISC-V ISA. All these cores come with tuned performance libraries. Without software being able to use this, it's pretty useless. And then it comes with the overall open source software ecosystem, which is RISE. This is an AI computation cluster, how it looks like. You got the AI core, which has the close coupled memory, AI acceleration functions built into the core that talks to the matrix multiplication accelerator through a shared memory. Again, these are high-speed memories, low latency, high-speed memories. So these talk to them, and the matrix multiplier keeps, operates at very high speed with a lot of data coming in on its own operations without having to worry about stalls and bottlenecks on the AI operation. So the hardware accelerator works closely with our AI core. And here, it need not be our own accelerator. Customers can plug in their accelerator. We'll provide a programming model for that. We'll provide the library, plug it in, boom. And you got your own differentiated AI offload engine working with our core. And now we provide additional interface, special interfaces that can, you can talk to the vector engine. If you want to talk to the vector engine, you can do that directly to the accelerator. So there are other custom features that come with it that makes integrating a customer AI solution or an AI accelerator into this RISC-V core to build a nice full-blown system. Here's an example integration where now we take a customer engine. In this case, it's a compute and memory engine. So it's a new architecture. And we put it together with our AI core, Akeana 1000 series, other accelerators, matrix. I mean, it's basically like a mix and match. You can do all these things, mix and match. And you can create your own custom subsystem or AI compute subsystem. And we have provide the interconnect or the shared memory to be able to have all these pieces talk to each other. Again, this is a software view of how a system like that will be used. I mean, we use the YOLO 3 tiny software library. You can see, the Akeana 1000 cores do the pre-processing and the post-processing of the software layers. Now, the conversion layers 1, 10, and 13 use the int8 and BF16 that our gem engine does. Then there's a customer says, no, I want a targeted acceleration engine for all the other layers. You can plug it in, and they all work together and create a full-blown system that is heavily optimized, highly performant. Performant per watt. I mean, this is, okay, and this is a multi-cluster system that we can put together. Now, that's the other capability we provide. I mean, there are customers who say, we want to provide these clusters and keep them as separate clusters, and we want to connect them together and to create a large data center class system. We provide the necessary interconnects to be able to connect these clusters together and connect within the cluster and then connect the clusters together. I mean, it comes with a closely coupled memory. There's a data prefetch engine, shared low latency SRAMs, model data pipelining, accelerator IP. I mean, they don't collide with each other. You can have really wide data bus width. So all of those work together very easily. So one other thing, right, we talked about custom instructions. The value of the custom instructions is, especially when you have nonlinear functions, which is what AI heavily uses. We see using these custom instructions. So there is, RISC-V provides native vector operations, but when we add our own custom instructions like FP16, FP, int FP8, TF16, we see nearly a 10x performance increase. Now, that's what we have seen. So they are, again, significant value. And one of the things, we looked at the data, and the accuracy using these hardware, it's like 100% accuracy match. So the data you get matches what you would expect out of a PyTorch library. Without losing fidelity, you get a 10x performance increase. And we provide the necessary performance libraries, software libraries to it. This is another softmax. Softmax, if you don't know what it is, it's a function that basically, when you do AI, lot of AI compute, you get a lot of data that may not be valid. So softmax is one of the functions that decides, the value of the data, process data that you get. And to be able to speed it up, you need like wide vectors, you need the nonlinear action of acceleration, and also the data movement engine. And we have all these different pieces. And as you can see the speed up, as we try the different NN models, we see somewhere between 2 to 4x speed up when we move from a 512-bit vector width to a 2048 vector width. So again, significant value add if you're building a AI system. A little bit quickly, I'll browse through them. I mean, this is our gem engine. It can support 32 by 32 array, 64 by 64, scalable. We support different data types, BF16, FP16, MXFP, int8. I mean, you can see it can scale from somewhere between 1024 Mac in this case is multiply add compute per clock to up to 4096. And with a very high utilization. I mean, our utilization for these blocks with our heterogeneous system is 95% or higher. And that's pretty amazing, which means that your AI compute engine is operating at max capacity most of the time. I mean, this is a little bit more about the systolic array. We talked about it. Different data types we support for our AI engine. You can see from the 64-bit all the way to the 8-bit, and different formats, FP, TF, MX, BF. all different formats. Some of them natively both input and output. Some of them we converted in the input only. But it can take all these as inputs and get the limited outputs, different outputs that you want. So, I mean, we talked about, okay, we got all these pieces, we got IP. How do we know what architecture, system architecture works for us? What is the best way to do it? So we provide different modeling platforms where you can actually take it all, put it together, try it out, and run some software. You can use it as a software development vehicle, or you can run, if you have software existing, run performance benchmark, and try to figure out what actually works well for you. And this is a very powerful capability, because then you can define your own AI compute subsystem that gives you the best performance for your best feature needs for your applications. I mean, you can see hardware, regular RTL supports the simulation EDA tools. We provide like C++ system C library, software guys love it. The cycle exact, cycle approximate, then we provide a software simulator, which is purely an instruction set simulator, all the way to the QEMU, which is it's like a emulation, it's like a virtualizer, which can be used to port software at a very high speed. So it's a wide range, and now when you start a development, you start from the QEMU, and then you just go down towards your left all the way to the hardware RTL in different stages. And in the hardware RTL, we also provide emulation and FPGA capabilities, so you can run your software at very high speed in emulation FPGA. Especially useful for bringing up software, tuning software performance, make sure your system architecture is performant and works well with the software. So we talked about these pieces, so I'm going to walk through a sample AI subsystem put together, right? Now what we have done is that, and this is actually something we built. Now we took a data movement control core. We put, I mean, it was scalable from 1 to 8. We created a 2-core data movement cluster. Then we went into the compute. We created a compute cluster of like 2 cores, gem engine, 2 to 8, all connected through 2 types of interconnects. Now, again, we have our own interconnects, AMBA-based interconnects. So you got the data movement cores using a narrower width, and then you got the AI compute cores that use a wide width. The wide width talk to the local SRAM banks, which are low latency, high speed, and then the narrow width talks to the DDR. No, it's a longer latency. And we got a DMA engine. While everything is operating, we got the DMA engine to supply data from the DDR into the SRAM so that our compute engine constantly has data to keep operating without any blocks. So how do you verify something like this? I mean, it's all nice. So what we did is that we put together, took this subsystem, put it in an emulation. We also did simulation. We connected a JTAG because you're running software, so you need a software debugger. We have a UART, so you can do text-based printing, track software runs. Connected to a terminal. We got an actual software debugger. Then we had an AI data set, and I'll talk a bit about how we did the AI data set. That will feed in patterns into the DDR, load the actual programs into the DDR with the data, with the vector AI compute data. So we preload it in the DDR, fire it up, and then let the software run, and you can run a full-blown software. What we did was created a mini AI system that you can run full-blown software. Here's a bit about how we did the AI compute. One of the things about that is that you have to generate. If you're not running actual full-blown software, you need to be able to run some what you call vector data that is relevant. So the way we did it was that now while the emulation engine is running the pattern, we'll be offline generating the data. So these are running in parallel. So you got the offline data generation happening in parallel with the DUT execution. So once the DUT execution is done, it dumps it out, and then it loads the next one, and it just keeps running. And we set it up so it runs 24/7, that it's constantly running. You get a lot of validation doing that, in this whole subsystem. Gives you a lot of confidence on the functionality of the area. So again, putting it all together, I think I talked about it. Just a summary, you got all the different pieces that you need to put together AI, compute and data subsystem, full-blown AI silicon, right?
Okay, do we have any questions? We can have a 5 minutes Q&A if any doubts or questions to be asked. Yes. How GEM device will improvise the
Yes. Design.
improvise the design of Akeana?
AI system, GEM is. The question is, when we talk to customers, some customers say, hey, we have our own GEM engine because that is our secret sauce. So we add that. But there are customers who say, this is our need. This is what we want. This is our spec. This is our, performance power area need. Build the architecture and build this for us. So there, we actually use our own GEM engine and build the whole architecture. We just take the subsystem and build the software for it, tune it, take it out and build it.
Does it have any impact on the power utilization factor also?
So the key is, right, okay, so the power is directly tied to how much data you want to process in terms of performance, right? So yes, your GEM is operating at a constantly, right? So there is going to be power consumption. Okay, so GEM is operating constantly. So there is. So the way our implementation is, it's already power and performance optimized. So you can scale it down to a lower frequency if you don't want the high frequency. And because it's wide, you can actually send a lot of data through it without any issues. Again, we use heavy clock gating and all the necessary power features that any hardware would use. It's all built into the IP. So that gives you the best power optimized performance. Yeah.
Hi, my name is Kiran. I'm the co-founder of AI Cairo. So we are an AI consulting startup. Two questions. One is, if the future of AI adoption is going to be that companies are going to have AI farms, how are you addressing the governance part of it?
Can you repeat it?
The governance part of the
Before
models.
that, is that AI what? AI?
So let's say enterprises are going to move into a space where they're going to use multiple models.
Okay.
Okay, it could be their own foundation model sitting in their own inferencing center. It could be API access, or it could be hosted on the cloud. So it's going to be what we believe is the future is going to be very similar to what we call as server farms. You're going to see model farms within enterprises. Now, how are you looking at governance, number one, particularly in terms of the behavior of these models, especially with trends that you're seeing around drift and context shift that's happening specifically into LLM models?
Right.
Thank you.
So it's a great question, right? So that is where the heterogeneous architecture come into the picture. So you can build silicon at that low level that are targeting specific models if you want, right? So then what happens is that instead of one dual system or one dual architecture, at the base level, it is still the same ISA, but you can have different pieces targeting. Like for example, we showed an example where each processing engine targets a different set of layers. And you can create more and more. The capability is just endless. It all comes down to the system architecture at that point. Say, looking at the whole software stack, we want to build a data center that is targeted towards these type of models. You can custom build. And you can build an architecture that works extremely well on this, on specific types of models. Now, obviously, you want to also have some scalability because you don't want to just say, it can only run this model and anything else is not going to run. So that is where the system architecture comes into the picture. Again, RISC-V provides the capability, so. Yeah, we should talk.
Any more questions do we have, ladies and gentlemen? Asking again, do we have any more questions to be addressed or asked?